After studying this module, you shall be able to know about the various reactions of metal carbonyl compounds, learn about the effect of nitrosyl on metal carbonyl complex, identify the nucleophilic and electrophilic centers in MCO complexes, analyze the action of heat on the metal carbonyl centers. The metal carbonyls exhibit a wide variety of chemical reactions that we all know. Some or all the carbonyl groups can be displaced by other ligands with varying degrees of back acceptor abilities such as phosphines and alkyl isocyanides. The photochemical reactions of metal carbonyls often occur cleanly and easily. The photochemical reaction of metal carbonyls may lead to loss of carbonyl or fission of MM bond. The free CO molecule is not attacked by nucleophile under normal conditions. The coordinated CO can be attacked by a variety of nucleophiles such as hydride, hydroxyl, alkyl, alkoxy, etc. The positive charge on a metal carbonyl increases its reactivity towards nucleophilic attack, and it can be attacked even by weak nucleophile such as water. Dinuclear metal carbonyl reacts with H2 at high temperature with cleavage of MM bond. Metal carbonyls react with NO forming metal carbonyl Nitro Cells. Metal carbonyl are oxidized by halogens to metal carbonyl halides. Metal carbonyls are reduced by sodium, sodium borohydride and many more to metal carbonylate anions. The number of metal carbonyls is very large. At the same time, the metal carbonyls exhibit a wide variety of chemical reactions. However, we can discuss few important chemical reactions of metal carbonyls. All reactions of carbonyl ligands depend upon the polarization of the CO on the binding to metal. Let us see some reaction in which we have CO substitution. It is the most common class of reactions of metal carbonyls in which some or all the carbonyl groups are displaced by other ligands. The incoming ligands may be individual donor molecules with varying degree of back acceptor abilities themselves, such as phosphines, alkyl isocyanides and unsaturated organic molecules such as benzene, cycloheptatriene, pyridine and many more. Some ligand substitution reaction of metal carbonyls are, in the first reaction we can see the nickel carbonyl complex on reaction with triphenyl phosphine undergoes substitution reaction giving nickel carbonyl whole twice and triphenyl phosphine whole twice and release 2 carbon monoxide molecules. In the second reaction, we have an octahedral complex of chromium which on reaction with pyridine gives a substitution reaction in which chromium has 4 carbonyl molecule and 2 pyridine molecule and release 2 carbon oxide molecule. If you see the reaction of nickel tetrahedral complex with NF3, no reaction takes place because NF3 has no pi accepting ability. The classical substitution reactions are more or less mainly thermal reactions. In many cases, they are not clean. For example, a pentavalent complex of iron is treated with triphenylphosphine, a mixture of product is obtained. In other cases, the thermal reactivity of metal carbonyls may be too slow. In some other cases, the catalysis of the thermal reactions by palladium oxide or hydrated cobalt chloride is effective. Vanadium octahedral complex of carbonyl is hyperreactive towards ligand substitution reaction because of rapid associative SN2 pathway. We can compare two reactions. In the first reaction, we have vanadium octahedral complex on reaction with phosphine gives vanadium pentavalent carbonyl complex with one molecule of phosphine and one release of carbon monoxide. In the second case, we have chromium octahedral complex reacting with phosphine giving again a pentavalent carbonyl complex and one molecule of phosphine releasing one carbon monoxide molecule. The reaction of vanadium complex is about 10 to the power of 10 times faster than that of chromium complex, that is, the K1 divided by K2 is equals to 10 to the power of 10. The exceptional reactivity of vanadium complex is due to the fact that it is a 17 electron system which is generally far more labile than a comparable 18 electron system. The exchange of carbonyl of metal carbonyls using labeled C14 carbonyl has been studied. In the case of nickel carbonyl complex, this exchange reaction takes rapidly, while in the case of iron carbonyl complex and chromium carbonyl complex and manganese carbonyl complex, it takes place very slowly. Let us consider the reaction. Nickel tetrahedral complex on reacting with label CO molecule gives nickel CO whole thrice and with one label CO molecule and with the release of one carbon monoxide molecule. The rate law of this reaction is given by rate is equals to rate constant into the concentration of nickel carbonyl tetrahedral complex. It means the labeled C14 carbonyl is involved in the first step and according to which the mechanism which is suggested is as follows. The nickel tetrahedral carbonyl complex first gives nickel trivalent carbonyl complex with the release of one carbon monoxide molecule, which is a slow step. In the second reaction, this trivalent nickel complex combines with one C14 labeled carbonyl molecule and gives NiCO thrice and one labeled C14 carbonyl molecule, which is a fast reaction. The intermediate NiCO whole thrice involved in this reaction has been isolated by the photolysis of nickel carbonyl tetrahedral complex in an inert matrix at low temperatures. Let us see some photochemical reactions. In the recent years, increased attraction has been given to photochemical reactions. The photochemical reactions often occur cleanly and easily where the corresponding thermal reactions are messy and unavailable. The photochemical reactions of metal carbonyls generally take place through two primary photoprocesses. The one is the photoejection of a carbonyl ligand. Two is MM bond fission. In the actual practice, all the metal carbonyls can undergo loss of one carbonyl group forming an electronically and coordinatively unsaturated reactive intermediate. This is due to the fact that the lowest energy electronic transition in metal carbonyl is pi to sigma star, which weakens one or more MCO bond leading to CO loss. On the other hand, nearly all the MM bonds have a strong absorbing transition, that is sigma to sigma star, which generates MCO whole X radicals. The photogeneration of MCO whole 5 from MCO whole 6, where the metal is chromium, molybdenum and tungsten, has been studied extensively. These 16 electron metal carbonyl complex fragments react readily with the available donors to form MCO whole 5 L species. If L is a bidentate chelating ligand, the reaction continues to form MCO whole 4 L complex. The MCO whole 5 fragment can even combine with the species which are regarded to have no donor ability, such as neon, argon, xenon and methane. These products normally cannot be isolated. However, chromium carbonyl xenon complex has been characterized at -100 degrees centigrade by IR spectroscopy, and there are many more complexes which has been isolated. The photochemical reactivity of cobalt carbonyl complex may also be attributed to the radical intermediate, which may also be produced thermally at relatively lower temperatures. The photolysis of some lower metal carbonyls yields higher metal carbonyls. You can see from these reactions of iron complex, osmium complex, and there are other reactions also. Now let us see some nucleophilic attack on carbonyl molecule. Free CO molecule is not attacked by the nucleophile under the normal condition. If you combine a CO molecule with hydroxyl, you can find that there is no reaction which takes place. However, free CO molecule is not attacked by nucleophile under more rigorous condition, such as 125 atmospheric pressure and 400 Kelvin temperature. This is due to the following reasons. 1. The bond length of CO molecule is small, that is 1.131 angstrom, and its pi electrons are held tightly. Second, the polarity of CO molecule is low, that is its dipole moment is 0.23 dBs, and the carbon atom is only slightly positively charged. But when the CO is coordinated to a metal of low pi basicity, the carbonyl carbon atom becomes positively charged because the carbonyl to metal sigma donation is not compensated by metal to carbonyl pi acceptance. As a result, the pi star molecular orbitals of the coordinated CO are open to attack by the nucleophile. Here, in this reaction, metal carbonyls reacts with the nucleophile. Then this nucleophile gets attached with the carbonyl carbon and the metal carbonyl anion is generated. You can see from this reaction we have various attacking nucleophile such as hydride, hydroxyl, alkyl, and alkoxy nucleophiles. Attack by hydride ions. The attack on coordinated CO by hydride ion produces metal formyl, which is unstable and loose CO forming metal hydride anion. In the reaction given here, where the pentacarbonyl iron is reacted with tetrahydroborate anion, this is a hydride addition reaction. Hydride addition to a carbonyl group can be achieved with compounds containing nucleophilic hydrogen atom and is known as reduction reaction. One such compound is sodium borohydride. The reaction involves the carbonyl group behaving as the electrophile and a pair of electrons from one of the BH bonds being transferred to the carbon atom of C double bond O group. The reaction can be regarded as hydride transfer. Attack by alkyl lithium. The reaction of metal carbonyl with alkyl lithium produces acyl complexes. So, in the reaction shown here, tungsten hexacarbonyl react with methyl lithium to form an acyl complex in which the methyl group gets attached to one of the carbonyl carbon, and in the next step it forms its resonating acyl ions in which metal carbon bond is doubly bonded and CO bond is now singly bonded, as you can see from the reaction mechanism given here. Attack by hydroxyl ion. The attack on coordinated CO by hydroxide ions produces metal carboxylic acid, which is unstable and loses CO2 forming metal carbonyl hydride anion. The latter produces neutral metal carbonyl hydride on acidification. You can see from this reaction mechanism, when chromium hexacarbonyl is treated with a strong base such as sodium hydroxide solution, a bridge hydride complex is obtained instead of the expected product, which is chromium CO5H. This anion, on further treatment with chromium hexacarbonyl, gives metal carbonyl hydride of chromium. You can see from this reaction mechanism. Attack by water. The positive charge on MnCO octahedral complex makes it very sensitive to nucleophilic attack, and even water molecule can attack on its CO group. So, in the reaction shown here, nucleophilic attack of water on manganese hexacarbonyl is done. Water molecule is attached on one of the carbonyl carbon. This is on further rearrangement gives metal carbonyl hydride. You can see from this reaction mechanism. Now we see the electrophilic attack on CO. The carbonyl group is a polar functional group that is made up of carbon and oxygen, which is made up of double bond of carbon and oxygen. Let us see the electrophilic attack on carbonyl. The carbonyl group is a polar functional group that is made up of carbon and oxygen, in which they have a double bond. There are two simple cases of carbonyl group: aldehydes, where the carbon atom of the carbonyl group is bound to a hydrogen, and ketones, where the carbon atom of the carbonyl group is bound to two other carbons. Since The carbonyl group is extremely polar across the carbon-oxygen double bond. This makes it susceptible to addition reactions like the ones that occur in the pi bond of alkenes, especially by nucleophilic and electrophilic attack. CO is a weak Lewis base and it can form adducts with the strong Lewis acids such as boron halides and aluminum hydrides. You can see from this reaction that the adduct is forming. The metal carbonylate anions may exhibit strong interaction of the type which is or the similar ligands, and M prime is the transition metal. In addition, electrophilic attack by H plus and Me plus and other carbocations can occur especially on bridging carbonyl groups. An example is given here. You can see from this example. Now we will see the action of heat. The mononuclear metal carbonyl decompose into the metal and carbon monoxide on heating. Nickel complex on heating at 200 degrees centigrade gives the nickel metal and 4 CO molecules. Similarly, your FeCO5 on heating at 250 degrees centigrade gives Fe and 5 CO molecules. A lower metal carbonyl can be transformed into a higher metal carbonyl on heating up to an appropriate temperature. You can see there are more reactions given here. When the solution of FeCO9 is heated up to 70 degrees and then cooled, green crystals of Fe3CO12 separates out. Reaction with hydrogen. Dinuclear metal carbonyls react with hydrogen gas at high temperature and pressure, forming metal carbonyl hydrides with a cleavage of metal-metal bond. Mn2CO10 on reaction with hydrogen gas at 200 degrees centigrade and 200 atmospheric pressure gives 2 molecules of MnCO5H. Reaction with halogens. Most of the metal carbonyls react with halogens forming metal carbonyl halides. FeCO5 complex on reaction with iodine gives FeCO4 and 2 iodine with the release of 1 carbon monoxide molecule. Another complex of molybdenum with carbonyl gives on reaction with chlorine MoCO4 and Cl2 with the release of 4 carbon monoxide molecules. Some metal carbonyls are decomposed by halogens forming metal halides and carbon monoxide. You can see the cobalt carbonyl complex on reaction with chlorine gives 2 cobalt chloride and 8 molecules of carbon monoxide. Similarly, nickel carbonyl complex on reaction with bromine gives nickel bromide and 4 carbon monoxide molecules. Reaction with nitro cells. Many metal carbonyls react with nitric oxide gas to form metal carbonyl nitro cells. NO acts as a 3-electron donor ligand while the terminal CO acts as a 2-electron. The bridging CO and MM bond contribute 1 electron each to the electron count of the metal. 2 nitrosyl molecule can replace 3 CO ligands of a metal carbonyl without affecting the electron count of metal. You can see from this reaction of iron complex. One NO molecule can replace two bridging MCOM linkage and one MM linkage of a metal carbonyl without affecting the electron count of metal. You can see from this cobalt carbonyl complex reaction. One terminal CO and 1 mm bond of a metal carbonyl can be replaced by one NO molecule without affecting the electron count of metal. You can see from some of the reactions given here. Let us see some oxidation reactions. The reaction of metal carbonyls with halogens or alkyl halides may be regarded as oxidation reaction because the oxidation number increases from 0 to +1, +2 and so on. For example, in a reaction of iron pentavalent carbonyl complex on reaction with iodine gives iron CO4 I2 complex with the release of one carbon monoxide molecule in which the oxidation state of iron changes from 0 to +2. You can see some other examples also. Reduction reactions. The reaction of metal carbonyls with sodium metal in liquid ammonia or alkali metal amalgams in THF or sodium borohydride in THF leads to the reduction of metal from the oxidation number 0 to -1, -2 and some more, forming metal carbonylate anions. You can see from the reaction of chromium carbonyl complex on treating with sodium and liquid ammonia gives a complex in which the oxidation number of chromium changes from 0 to -2. There are many other reactions you can see in which the oxidation states changes from 0 to either -1 or -2. Now let us summarize what we have learned in this module. The large number of metal carbonyls exhibit a wide variety of chemical reactions. The Ligand substitution reaction of the metal carbonyls are the most important reactions in which CO group can be replaced by other ligands having pi accepting abilities such as phosphines, Nitro Cells, etc. The photochemical reactions of metal carbonyls may lead to loss of CO or fission of MM bond. The exposure of pentavalent iron complex or osmium complex to UV light leads to the formation of dinuclear metal carbonyl. Free carbonyl molecule is not attacked by nucleophile under normal conditions. However, free CO molecule is not attacked by nucleophile under more rigorous conditions such as high pressure and temperatures. Coordinated to metal of low pi basicity is susceptible to nucleophilic attack. The positive charge on a metal carbonyl increases its reactivity towards nucleophilic attack. The metal carbonyls are oxidized by halogens to metal carbonyl halides. The metal carbonyls are reduced to metal carbonylate anions by sodium in liquid ammonia, sodium amalgam in THF or sodium borohydride in THF. The metal carbonyls undergo thermolysis in different ways. The mononuclear metal carbonyls are decomposed on heating to a certain temperature. A lower metal carbonyl can be transformed into a higher metal carbonyl on heating up to an appropriate temperature.